case you guys need a refresher, guess what? This is the section for you guys. Chain rule. How is chain rule applied in space? All right. So let's just do a quick little example of the chain rule in single variable. So let's find dy dx of this. So easiest way to remember chain rule is derivative of the inside times the derivative of the outside. So for example, a lot of times in your books, or depending on your professor, they rewrite this thing u equals 3x minus 7. So therefore, on the outside, it's going to be u to the 5th. And you take the derivative of each one individually and just put them together, right? So the derivative of u to the 5th is going to be 5 u to the 4th. Derivative of just u here is just going to be 3, right? Because everything else goes away. And then you just put them together. So then dy dx is equal to this. So 5u, which was just 3x minus 7 to the 4th, times du, which is all of this, which is just 3. Or again, the general equation you see that. So that's our general rule in single variable. The cool thing is, same thing applies when it comes to multivariate. So the only difference is, unfortunately, we have a couple different cases of the chain rule. So let's do the first one. So suppose z is some function with x and y, and with differentiable functions x and z, where x is g of t and y is h of t. So two different functions with respect to t, and they're both differentiable. Then z is differentiable at t by our chain rule equation. So lots of stuff happening here, right? All right, so a lot of stuff. So you could kind of break this down into this part right here is zx. This stuff right here is tx, right? So t variable with respect to x. Zy, and then ty. That's our chain rule. So we're doing partial derivatives with respect to x and y of two different things. Okay. Of the function itself, and also the other two functions given to us with x and y. So let's try an example so you can see exactly how this would work. Okay. So let's find the z dt of the function z is equal to that, where x is sine x and y is secant x at the point t equals 0. Okay, so I kind of gave you guys a little hint on how to break this down, right? So we want dz dt. So the first part of this is we want to find the derivative of this with respect to x only. Okay. So we'll just make a little column here. So d z dx here. So taking the derivative only with respect to x. Should give us that. And since we need the same thing, we'll just say cy itself. So again, only with respect to y. Gives us that. Okay. Now we'll go to the t's. So here is tx. So going to here, only in the x here, taking the derivative there. So that's just going to be cosine. And then ty, going over here and taking the derivative with respect to y, or t itself, right? Just the y value. And that's going to be secant tangent. So now we put everything together. So the coordinate equation is going to be zx. So y to the third minus 4 y to the fourth x times tx, so cosine t, plus the z with the y's times ty, so secant tangent. So that's our general derivative. But the good thing is we want at the point t equals 0. So if t equals 0, that means we're just plugging in t for 0 here and there. So t of x and t of y at the point 0. So cosine of 0, well, actually, wait. We need a couple things, don't we? Yeah, we do. Yeah, okay. So we'll start here. So cosine of 0 is going to be 1. Secant of 0 times tangent of 0 is going to be 0, because tan 0 is 0. Those are those portions. Now, we should be given an answer, one single answer back, right? Well, what's x and y going to be? We have no idea, right? So what does that mean? So this goes back up to here. So if I plug in 0 in for sine, so sine of 0 is going to be 0, so x is equal to 0. If I plug in 0 in for secant, what do we get there? Well, again, secant is 1 over cosine. So that's just going to be 1. Right? Because cosine of 0 is 1, so 1 over 1 is just 1. Okay. So there we go. So now that we know what x is and y is, now we could plug everything, well, for all three variables, x, y, and also t. Okay. All right. So this is not going to be plugging in some ones and zeros everywhere, right? Because including these values here. Well, we could have plugged them here earlier, but I should them just for practice sake. So y is going to be 1 minus 4 times 0. Cosine is 1 plus 3 times, so 0 minus also 0. So lots of zeros everywhere. It's going to be 1. Well, this is nice, isn't it? A lot of stuff cancels. So this is all gone. So we get 0. So we get 1 times 0, or 1 minus 0 times 1, which just gives us 1. Oh, we'll look at all that work just for simple 1. So that's how we use our chain rule. So let's try another example. Keep this up so you can see the mimicry of it. Okay. So again, find dz dt of our z function, x and y, and again, where t is equal to 0. So we do the exact same thing, so mimicry. So z of x, c of y, t of x, ty. Or you could replace that y of t or x of t or whatever. I just choose that because I remember I'm using the t values themselves. But an alternative to this, instead of saying ty, you could also say x of t, because you are taking the x value in respect to t. But whatever, each your own. Okay, so anyways, all right, so I'm going to rewrite this a little bit to make it look like this. It's just easier for me to when I take the derivatives. Yeah. So now if I plug in, so if I take the derivative with respect to x, so that's again the chain rule, right? So derivative of the inside times derivative of the outside. So derivative of the inside is just going to be y times the derivative of the outside is going to be 1/2 itself raised to the negative 1/2 power times y. And if you notice, zy is the exact same thing. Except with an x on the outside. Okay. All right, derivative with respect to tangent is secant squared. And you guys are going to love this one. The derivative of tan inverse is 1 over 1 plus x squared, or since we're dealing with t's, it's t squared. All right, and now we just plug in zeros everywhere. Right, so what's our point b? So I know t is going to be 0, so this time I'll just put it in point coordinate, make it easier. So if I plug in 0 for t, that's also 0. Plug in t in for tan inverse. Well, if you're not sure what that means, right? So we want to figure out y at tan inverse, so 0, or in general. So 0 is equal to tan y. So that's just going to be 0 as well. So just like last time, I'll put the general format. So according to our equation, leave that up right there. We get all of this fun stuff. And now we just plug in the point 0, 0, 0 everywhere. And hopefully we get an answer out. So this is why a lot of times t equaling 0 is no fun, because notice everything goes away, right? This is y 0 on top, so that's all gone. This is 0 on top, so that's all gone. Not fun, but that's our answer. Right, so it's just a quick little example showing you guys how to do so. You know, we can get much more complicated. You know, if t equaling 1 or, you know, t equaling 5, you can find any arbitrary value itself, right? Is it 0 end up being a nice number at the end? Because, you know, the work is actually just getting up to here, right? The plugging in the values, you know, extra step you have to deal with. Any questions? So let's do one more example before we get to case 2. And this example is an actual application. So you can see how the chain rule is done in application format. So if you guys have taken chemistry before, you probably recognize this example here. So the pressure P in kilopascals, volume in liters, and temperature in Kelvin of a mole in the ideal gas related by the equation PV equals 8.31 T. So if you guys remember, most famous equation, the ideal gas law. Find the rate at which the pressure is changing when the temperature is 300 degrees Kelvin, an increase in a rate of 0.2 Kelvin per second, and the volume is 100 liters and is increasing a rate of 0.4 liters per second. So it's a lot of stuff happening. So what's asked of us find before we do anything, right? We want to find the rate at which the pressure is changing. So we want to find dP dt. That's what we're looking for. So because we want to find dP dt, first we got to figure out is just solve for for P. Make an equation of just P. So that's not that hard. And we do like that, right? Just divide over the Z, or sorry, the V. But I'm going to bring it to the top, just make it look like that. It just makes it easier when I take the derivative. Okay. So therefore, I need to find two things, just like we did earlier. We need to find respect to temperature and find respect to volume. That's like our X's and Y's. Okay, so the derivative respect to temperature is just going to be itself without a T. And now for the derivative respect to volume, is that. So therefore, our general equation is going to look like this. There we go. So get rid of that. Okay. Now, what is dt and what is dv? Well, the good thing is it's actually given to us in the question. So we know that the volume is going to be 100. dVAT is right here, 0.4. We're also given temperature to be at 300 Kelvin, and dt is changing from 0.2. So now just plugging in these four values into our equation and just slowly breaking it down, right? We could find the change of the pressure with respect to time, and it's actually decreasing. It's in kilopascals, I believe. Yeah, kilopascals. It was decreasing, which is good. So, final example will show you guys how the chain rule is done in an applications process for the changing of stuff, because this will be much harder to do if you're just doing the old-fashioned single variable case. Okay, now let's go on to the second rule of the chain rule. What if instead the x and the y values were in two variables and not just one variable? So what I mean by two variables instead of one variable is something like this. So look at our last examples. It was x equals sine of t. It was a single variable. But what if we have two variables, s and t, respectively? Now, how do we find the derivative? Okay. And that goes on to our second chain rule case. We're actually going to do it twice. Don't worry. It gets a little messy, especially for the third rule. So suppose z is some function with respect to x and y and differentiable at x and y, where x is some function g with respect to s and t, and s and y is a function with respect to s and t as well. And again, both differentiable s and t. Then the derivative of z is equal to these two parts put together. So it's actually two different derivatives together. Okay. So we're doing lots and lots of derivatives today. So again, I'm going to give you guys little shortcuts. This is going to be f of x. This is going to be x at s. F of y. y at s. So the partial's there. And same thing on the other side. T, sorry, this is the t. So we're going to find 4 different derivatives, 4 different partials, and then put everything together. Or actually 6, but yeah. All right. So let's try this equation out. Find dz ds and find dz dt when we have these functions put together. Okay. So let's just make our list down here. So we need all 6. So we'll just, start from the beginning. So looking at just this, partial with respect to x, partial with respect to y, and now we're just going to do 4 of them. So now we'll look at x first. So x with respect to s. So only with respect to s. So that means this goes away. We're just given t squared. Now we do partial with respect to t. That's going to be 2ts minus 1. And now we go to the y and do the same thing. It's going to be 6s squared t squared. And then with respect to t, be 4s the third t. Okay. All right. Now that we have all that information, now we just plug it in where they're supposed to be. So first we'll do d cds. We'll just follow this template above. So this function times s of s plus this one times y of s there we go. So 1 down, 1 more to go. So notice a good thing, it's a mimicry of itself, right? It's the same template. The only difference now is it's going to be respect to t's here. There we go. Those two are our actual chain rules together. So not individually, all put together. And again, if you given a point, if t equals 0, you would do the same thing. So this is not a part of it, but like if t is equal to 0, we plug in 0 everywhere and see, we just insert each one. We find dz ds, dz dt at 0, at t equaling 0, right? That would probably be an extra step there. Now, what makes this so interesting is, well, you don't have a third rule, which is the good thing, right? But what if this goes on in general, or the general chain rule? Meaning, what if we have it for 3 variables, 4 variables, 5 variables, 6 variables, and variables? What that means is the x value has, n different variables, and same goes with the y. Oh, actually, it's supposed to be the same. Sorry. Right, instead of just 2 now. Okay. The good thing is it's just like a train. We just keep adding on, adding on, adding on, adding on, adding on, and adding on. Okay. And again, we're always going to have, depending on each individual variable, the du, d, d1, d2, dt, the fourth, and di term. Okay. So it literally is just like a chain block. Okay. So this represents one single variation of it. So if we have 3 dimensions or nth dimensions, we'd have one and then another one, respective with the second one, third one, fourth one, and fifth one, until we finish all of variables with respect to it. Okay. So what this means is a lot of the times they're not going to make you find the derivative. They're just going to ask you to just express what it would look like. Okay. So for example, here, let's do a 3-dimensional one. So let's suppose we have our surface of a equaling with a function with respect to x, y, and z, and where x is the function at x of u and v, y is another function of u and v, and z is another function again with u and v involved. What we want to figure out is what would the general chain rule look like using these variables itself, right? The theoretical chain rule. Now, how this goes about is we're going to have 2 processes, dA du and dA dv. Okay. Now, what I mean by that is if this had 3 variables, u, v, and w, we would have another one called dA dw. So that dictates how many equal signs we're going to have, is how many variables we have in the x, y, z, or whatever letters they decide to choose from. So whatever it's respect to in the individual x, y, z's, that's how many we're going to have down here. Okay. All right. Now, what dictates how I'm going to have much here dictates how many variables we have there. So since we have 3 variables, we're going to be adding 3 different things together. Okay. And it's going to be the combination of all 3 put together, right? So for example, since we want du, everything is in terms of u. So first it's going to be df dt, or sorry, dx, right? The partial derivative of f of x times dx du. So this is all of the x variables plus dy, df dy. So the partial derivative of y times dy du plus, and now we finally do the z's, df dz times dz du. And there we go. We're done with that one. And now the next one is a mimicry of what we just did. The only difference is we just have dv's instead of du's. So if we had if we had a w, it would be the exact same thing, but at the bottom we'd have dw's now. So we'd have an extra third one down here. There we go. Any questions there at all? No questions? Okay. So let's try to put this to practice. So we have the equation run above us right here. So let's put this to practice now. well, partially to practice, just to say. Yeah, that right there. Okay. So if u is equal to this, x is equal, y is equal, and z equal respective to each one individually, we want to find du ds when r is equal to 2, s is equal to 1, and t is equal to 0. Okay. Now, we only need one of these, not both of them, right? We're only looking for du ds. Okay. So you can kind of pretty much pick like one of these, and that's what we're going to be doing. Okay. So following the template, we need to find the partial of the u function with respect to x, y, and z, and the partial with respect to s of all the other ones with respect to x, y, and z in those equations. So let's just go down the list. So again, it's u because it's u equals instead of z. So u of x, u of y, and u of z. That's going to go up right here in our equation. That's what those numbers are going to be. Okay, so partial with respect to x. So it's going to be 4 x to the third y, and everything else is gone. Partial with respect to y, so it'll be x to the fourth plus 2yz to the third. Partial with respect to z, so that's gone. So you get 3z squared, y squared. Okay. Now we can do x, y, and z with respect to s only because we want s, right? That dictates what we want here. So s, x of s, y of s, and z of s. And that's going to go there. All right. Derivative with respect to s only. So it's just going to be r e to the t. Because notice we have 3 variables, right? Oof, that's going to be a long one. We have to do all this fun stuff. Okay. This one's going to be respect to s only. So 2s r e to the negative t. And then finally, again, with respect to s. There we go. All right, that wasn't too bad. Okay, so remember, the good thing is they give us a point R2, S1, and T0. So all we're going to do is plug in everything respectively what we have. Okay, now we have X's and Y's and Z's everywhere, right? So we have to go back over here and see what each one is going to equal respectively. So if I plug in R to be 2, S to be 1, and T equal to be 0 into each one. So let's see what happens here. So e to the 0 is 1. So it'll be 2 times 1 times 1. That's gives us 2. Same thing process here. E to the 0 is just 1. Doesn't matter if it's negative to t, right? It's going to be 0. So we have 2 times 1 squared is still going to be 2. All right, sine of 0 is 0. So everything just goes away. So now we have our 4 terms. Or sorry, our 6 one. 6 numbers we have to plug in respectively. Okay, so let's see what we have. So plug it in 2 and 2, because it's only respect to x and y. So plug it in 2 and 2. I should get 64 out. Right, so 2 to the third is 2 times 2 is 4, 8. 8 times 4 is 32. Times 2, 64. Now plug in x, y, and z. So the good thing is z is 0, so that just goes away. So it can be 2 to the 4th power. So 2 times 2 is 4, times 2 is 8, times 2 is 16. This one again is only respect to z and y, but z is 0, so all goes to 0. All right, so e to the 0 is 1. 1 times 2 is 2. E to the 0 is 1. So 2 times 1 is 2, times 2 is 4. And then finally, this is going to be 0, so it's t to 0 is 0. Or sine of 0 is 0. Okay, now let's follow this template. So du ds. Okay. So first, it's going to be this number times this one plus this one times this one. Where am I? Yeah, this one plus this one times this one. And now at this point, right, we just multiply and add together. I got 192. Now, if you wonder where these numbers come into play, the general rule would look like this. So that's where all these numbers come into play, right? So I just follow our template, but have it above. Makes it easier. Okay. Now let's torture ourselves. Because everybody, when it comes to math, you're not doing it right if you're not torturing yourself. Given z is equal to f of xy, where x is in terms of r and s, find dz dr, and then find dz squared over dr squared. So the second partial derivative of that. Now, how that's going to come into play. Okay. All right. So now remember, we're only looking for r, so we do not care about ds, right? Just r. So it's just half of the work. Trust me, half the work is going to be painful already. Okay. So first, actually, so let's just first off what we did last time. So let's respect to z of x and z of y. Now remember, this is a general, so it's just going to be dz dx, and this is just going to be dz dy. Now we take the derivative of respect r of the x and y components. So this is just going to be 2r, and this is going to be 2s. All right, so we did this earlier. So dz dr is equal to this times dx dr. I'll write the general rule, then I'll plug in the numbers right now. So therefore, and the good thing is we actually have a number for this, right? This is just going to be 2r. Gives us that as well. Okay, so we're done, kind of. That's the first part. So now we have to find the second partial derivatives with respect to r. Okay, so we'll take the derivative now. So this would be dz squared over dr squared. Okay, so now unfortunately here, and actually every single term, it's going to be chain rule. Yeah, gotta love it, right? So we're going to have dz dx times 2r times the derivative with respect to r plus dz dx. So this is the derivative of this part. That's the partial there, if you guys are wondering. Times now the derivative of 2r, which is going to be 2. But it's like a product rule. And we keep going for the other part here. So plus v dy times 2r times the derivative of this, which is be d dy. Plus dx dy times 2r, or sorry, 2s. 2s. There. Now, okay, how do we put stuff together? So putting these stuff together there, and where's the other one? Oh, here. This stuff together there. This is going to give you exactly what we want. X, sorry, X. Do we want to do that way? Yeah, I want to do that way. And then putting these together, I'll put those to the side. You'll see what I'm about to do right now. Okay. Now, the problem what we have now is we have a couple of things happening.